Markov process is a process satisfying the Markov property and with transition operators that satisfy the Chapman-Kolmogorov equations everywhere. That is to say, we have transition operators q of r and t between any two times r and t, such that q of rt is equal to q of rs times q of st whenever r is less than or equal to s is less than or equal to t, where at a fixed time qtt is just the identity operator. This is analogous to describing the progressive distributions of a sequence of independent random variables on a state space S like this. If mu n is the law of the first n random variables, then we have this law here. Mu n times mu m is mu n plus m. Now, thinking of that context, in earlier lectures, lecture 16, we considered the reverse question. Suppose that I have a sequence of measures on the state space, and I'd like to construct independent random variables that have those as the distributions. Alternatively, I could phrase that in terms of the progressive products of those measures. And then the question is, suppose that I have measures mu n satisfying this property here. Can I always find an infinite sequence of random variables with mu n being the law of the first n of them? Now, the answer to that was yes, and the proof technique was what we called the Kolmogorov Extension Theorem. We explicitly constructed that sequence of random variables as the coordinate random variables on an infinite dimensional product space. We took the state space and took its product over the natural numbers. That is, the outcomes in that probability space are functions from n to s, infinite sequences in that case. And we constructed a probability measure on that large space from this consistent family of marginal distributions on subsequences in that space in order to construct our sequence of independent random variables. In this lecture, we're going to do something very similar, but in the context of Markov transition kernels. We're going to construct an infinite dimensional path space, probability space, on which the coordinate random variables give us a Markov process with these as our transition kernels. And to be precise, we start with a collection of Markov transition operators, which means that they satisfy the Chapman-Kolmogorov equations on a state space, SB. We're going to construct a probability space and a Markov process on that probability space, such that for any initial law that we want, that process starts at time 0 in that law and has these as our transition kernels. The probability space is going to be built on this, the path space, the product of S over T, which might be an uncountable set like the positive reals. This just means the set of all functions omega from T into S, and thinking of T as an interval, we think of these things as paths, indexed by time parameter T, taking values in S. We're going to construct the process, analogous to the way we did for independent random variables, as the coordinate process. For each outcome omega, xt of omega is just omega of t. So if we want all of this to work out, what we need to do is construct a sigma field over this infinite dimensional space and a probability measure, which is going to be indexed by that starting measure nu. We'll get a different one for each starting measure nu, such that on that sigma field, this process is a Markov process with respect to the filtration that it generates, and has as its transition kernels the ones given by these transition operators that we started with. The construction very much mirrors the Kolmogorov Extension Theorem construction from lecture 16, and in fact we're going to use that theorem along the way as well. So let's start with the sigma field in question. Our probability space is this infinite product space, the space of all paths, functions from T into S. And we want to have an infinite product space over those. The way to do that is to take the product space generated by the projections. So for each fixed time T, we have the projection pi T from the path space, from a path here, back into the state space. Now, what is that projection? It just picks out the coordinate, the teeth coordinate, which in other words is just to say that pi t of a path omega is the value omega at t. It's the evaluation map, if you will. And then we define the product sigma field, product over t, to be the sigma field generated by those projections over the whole time interval. Now let's explore a little bit what this sigma field looks like. For any fixed t, we have pi t is a map from st into s, which is equipped with a sigma field, b. And so pi of sigma t consists exactly of the preimages under the projection map of sets b and b. So what does that preimage look like? It looks like the set of all points omega in the probability space, that is, the set of all paths that project into b at time t. In other words, it's just the set of paths that happen to be in b at time t. Now, these events are typical examples of what are called cylinder sets. That is, we're saying that the value at some particular time is in some set B, which you might think of as a disk, say, if this were in the plane. And so we're fixing the value to be in a disk there, and the values at all other times are unconstrained. And so that particular event is just the disk taking product over all of the other independent directions, which is a cylinder. Although usually a cylinder would just be a product with one other dimension, this is with infinitely many others. So that's our sigma field. It's the sigma field generated by all of these cylinder sets over B. And we're going to construct a probability measure on that product sigma field in order to give us the right transition operators. Now remember from the last lecture that the transition operators tell us all the finite-dimensional distributions of the process. And so in fact what we'll do is we'll design this measure to match the right finite-dimensional distributions. Finite-dimensional distributions of the coordinate process just means finite-dimensional marginals of the measure. So let's fix a finite set lambda in T. The lambda marginal of our desired probability measure P is going to be some measure on this finite product space. And to say that it's the marginal of P is just to say that P pushes forward under the projection map to that measure on this finite product space. Now we don't have P yet, so what we'll do is we'll write down a set of marginals, mu lambda, for all of the finite sets in T, and then try to glue them together to form the measure P. But there's an obvious obstruction to doing that right away, because what if I have two marginals on two finite sets that overlap? Well, then they're going to have to agree somehow on the overlap in order for P to be consistently defined. So here is the precise consistency condition that's going to make that possible. Let's, instead of talking about an overlap, just talk about a containment. Suppose that I have two finite sets, lambda prime and lambda prime is a subset of lambda. In order for us to get a consistent glued together probability measure, P, from these, it's going to be necessary that if I take the measure on the larger set lambda and push it forward by the projection onto the smaller set, I should get the measure that I already defined on the smaller set. Now, to be very persnickety here, we should really be writing this as the projection on lambda prime, which is a projection from all of s to the t, restricted to s to the lambda. So we're really saying this, pushing forward mu lambda, equals mu lambda prime. But we won't write that every time and just talk about the projection, whether it's restricted or on the whole path space to start. So that consistency condition is evidently necessary in order to have a probability measure with all of these mu lambdas as its marginals. And the remarkable theorem, which extends the extension theorem we already proved in lecture 16, is that it's also sufficient. So here is the extended Kolmogorov Extension Theorem. If I have any standard Borel space as my state space and any time set t, if for each finite subset of t I have a probability measure on the finite product space s to the lambda, and all of those measures satisfy this consistency condition, that is, that if I take the marginal of a smaller set from the larger set, that's the same as the marginal in the smaller set from the whole path space, then in fact there does exist a unique probability measure on the whole path space which has all of those mu lambdas as its finite dimensional marginals. The proof of this is going to follow very much the way we proved the Kolmogorov extension theorem in the discrete case. You can think of the Komogorov extension theorem we proved in lecture 16 as the case where t is the natural numbers of this exact statement here. And the idea is the same here. We start by looking at an algebra, which is a sub-algebra of this sigma field, and it's just the union of all of the sigma fields generated by the finite dimensional projections. So that is, if I have such a finite dimensional projection, I'm looking at the sigma field of all preimages, pi lambda preimage of B, where B is in the finite product B times itself lambda times. Now, a union of sigma fields is typically not a sigma field, but it is an algebra because it's a union of algebras. It's also clear that the sigma field that that algebra generates is the full product sigma field, since this is the sigma field generated by just the projections pi t for each fixed t, and those are included here because among here we can take the singletons lambda equals to each time t, and we get included the preimages under all projections of B, which generate this thing here. So our game plan is going to be to construct a finitely additive measure on this algebra A, which has the right marginal properties, and then show that that finitely additive measure is actually a premeasure on this algebra. That is, it's countably additive over the algebra A. Then, a la the beginning of this course, that premeasure extends to a unique measure on the sigma field generated by A, which is the full sigma field we were interested in. And since it extends the premeasure, if we build the right marginals into the premeasure, they'll be there for the probability measure as well. So let's go ahead and define that finitely additive measure. I need to define the probability of any event A that's in this algebra. So an event A that's in this algebra has the form preimage under a finite dimensional projection of some set B. So lambda is a finite subset of the time space, and B is some element of the finite product of the state space's sigma field. Well, then that means I should just define this probability of A to be the lambda measure that I came equipped with of the set B. And since this is a genuine measure, this should be a measure as well, right? Well, hang tight. The first thing we need to do is see that this is even well defined. Because I could well have that A can be represented as the preimage under some projection of some set B, and also the preimage under some other set, lambda prime, of some other set, B prime. And so for this to make any sense at all, it better be the case that if this is true, mu lambda of B is equal to mu lambda prime of B prime. That's exactly where our consistency condition is going to come in here. So to see how this can happen, let's first note that these are finite sets, and so one of them is going to be smaller than the other, or they're equal in size. So without loss of generality, let's just assume that lambda prime is the smaller of the two. So that means that we can write lambda as some set of times t1 through tn, and lambda prime as some set of times s1 through sm, where m is less than or equal to n. Then let's just write out what these preimages are. The preimage under the projection pi lambda of B is just the set of all paths, omega, such that at the times t1 through tn, the vector omega t1 through omega tn is in the set B. And similarly, pi lambda prime preimage of B prime is the set of all paths such that omega at s1 through omega at sm is in this set B prime. Now how can those two possibly be equal? We're talking about two cylinder sets, where here we're specifying that at times t1 through tn we're in B, and then all the other times are free to roam. Here, s1 through sm are pinned down to have the values in this other set B prime, and the others are free to roam. And we're claiming that these two cylinders are equal to each other. How can they possibly be equal to each other? Well, the only way two cylinders can be equal to each other is if the top of one of the cylinders is a subset of the top of the other, and the other actually has the rest of the top just being product to make it equal to the first. That is to say, this can only happen if lambda prime is contained in lambda. So let's say that Si is equal to Ti for I less than or equal to m, and that the larger cylinder top of B is therefore equal to B prime times S to the n minus m. It's easy to see that in this situation, these two will be equal. We're saying here that the purportedly larger cylinder is actually equal to the smaller cylinder because the top of this larger cylinder is just the top of the smaller one, product with independent directions otherwise. But it is also true that this is the only way these can be equal by the argument that we just made. Because if there were some time in here that's not in here, and some time in here that's not in here, then this cylinder will have the full space S in that first time that's not in here. This one will have the full space S at this time that's not in here. And that shows that those two can't be equal in that case. So this is the situation in which we need to worry about well-definedness of this formula. So returning to the notation that we had from before, what we're saying here is that if I have these two preimages under different finite-dimensional projections of two sets being the same, then one of those sets is a subset of the other in the time space, and B is equal to B prime times an appropriate product of the state space. Well, in that case, the consistency condition that we imposed in the theorem tells us that the measure on the smaller lambda set, lambda prime of B prime, is the push forward of the measure mu lambda under the projection map. But that push forward is precisely defined by taking mu lambda of the preimage under the restriction of the projection to lambda preimage of B prime. But we can precisely describe what that preimage is. It's exactly B prime times this appropriate product of the state space, and that is precisely equal to B. So that gives us our well-definedness of the probability measure P. To be precise, it gives us our well-definedness of this function P on the algebra A. We need to see that it is a finitely additive probability measure to start. Well, for one thing, it's easy to see that its total mass is 1, because by the consistency we can compute this probability of S to the t as just mu lambda of S to the lambda for any lambda. But all of these are probability measures, so this one certainly has total mass 1. It's also a finitely additive measure. Let's see why. If I take any finite collection of events a1 through an in this algebra that are disjoint, well, by definition of the algebra, each aj is the preimage under some finite dimensional projection of some bj. Now this looks cumbersome because these are different projections for each j, but what we can do is define lambda to be the union of lambda 1 through lambda n, which is still a finite set since we're taking a finite collection of events here. Now bj lives in the sigma field tensor lambda j, and we can think of that as living inside b tensor lambda by taking bj prime is equal to bj times an appropriate product, that is the lambda minus lambda j, of the whole state space. And again, by the consistency condition that we assumed in the theorem, this will also be equal to pi lambda preimage of bj prime. Now I have a consistent pi lambda to use for all of the aj's. And now we note that, hey, these ones are disjoint. It therefore follows that these ones are disjoint, because if there were an overlap between two of these, then their projections would also overlap. So these bj's are disjoint, and therefore the probability of a1 disjoint union up to an is equal to just mu lambda, by definition, of b1 prime disjoint union up to bn prime. And since mu lambda is a probability measure, That's the sum, j going from 1 up to n, of mu lambda of bj prime. But mu lambda of bj prime is the same as p of aj. And so that shows that the p that we've constructed here is finitely additive. So we have a finitely additive probability measure on the algebra A, and by design it has the right finite dimensional marginals. That is, its lambda marginal is mu lambda. Now all we have to do is show that P is a premeasure. That is, that it's countably additive on A, because then it will have a unique extension to a full-fledged probability measure on the sigma field generated by this algebra, which is the full product sigma field we're interested in. Okay, so how do we show countable additivity? For a probability measure, that's equivalent to showing that if I have a decreasing sequence of events, an, that decreases to the empty set, then the probability of an tends to 0. That's all we need to show. Well, let's take that decreasing sequence, an. Again, an is in the algebra A of cylinder sets, and so it is the preimage under some finite dimensional projection of some set Bn. And we'd like to do the same thing we just did. We'd like to consider all of these as inside the same projected space, so we'll take the union of those lambda n's. One problem, though, that's no longer finite, but it is countable. So what we need in order to show countable additivity of this finitely additive probability measure is a countable version of the argument that we just made. That is, a countable version of the Kolmogorov Extension Theorem, which is exactly what we proved in lecture 16.2. So that's what we're going to use right now. By that Kolmogorov Extension Theorem, which held on any regular Borel state space, there exists for this set L a unique probability measure, which we'll call PL, on the space of paths on L and this countable product sigma field, which has these as its marginals. That is, if I take the projection from here onto here and push forward this big probability measure PL, then I get this marginal here for all finite subsets of L, including these ones that I started with here. Well, by the uniqueness all around, this measure PL has to agree with our finitely additive measure P on the whole algebra A. Why? Because the probability of AN is the measure mu lambda n of Bn. Now that is the push forward of the projection lambda n of PL of Bn by what we just wrote here from Kolmogorov. And that push forward is implemented by taking PL of the preimage under the restricted projection to L of Bn. But following the same idea as we used before, that restricted projection of Bn is equal to Bn times an appropriate product of the whole state space. That's L minus lambda n. And let's call that Bn tilde. So this says in particular that Bn is the projection of this Bn tilde under this projection here. On the other hand, An is the preimage of Bn under a different projection. And so if we compose those all together, what we get is that An is the preimage under lambda n of the image under the restriction of lambda n to L of this Bn tilde, where Bn tilde lives in the L-fold product of the state space. So if we reverse that, what that says is this Bn tilde can be written in terms of the An as the preimage under the restricted projection of the projection under lambda n of An. And now we see that since the ANs decrease to the empty set, so will the BNs, all living in the same space. After all, what we're doing here is taking this set, projecting it down into a finite dimensional space, and then taking a product of the state space and all of the other free coordinates. Since these ones are all shrinking down to 0, the whole thing, which is just a product of those sets with the other unconstrained variables, is also shrinking down to 0. And so finally that says that P of an here is just equal to PL of Bn tilde. The Bn tildes go to 0. PL is a probability measure by the countable Kolmogorov Extension Theorem, and therefore that goes to 0, which completes the proof of this Kolmogorov Extension Theorem. We have a unique probability measure on the full path space, which has any finite-dimensional marginals that we want, provided those marginals satisfy the appropriate consistency condition. Now, let's come back to our goal here. We were hoping to construct a Markov process on this path space with given transition kernels. And we're going to do that by using this Kolmogorov theorem. The result is that if I start with any initial distribution nu that I want on my state space, and I have my Markov transition operators, meaning that they satisfy the Chapman-Kolmogorov equations, then I can always find a unique probability measure on this path space. I'm going to index it by nu. We might also want to index it by the q's, but those will just be fixed in the background for reasons we'll see later, such that the coordinate process here, that is, the process which xt at a path omega is just omega at t, is in fact a Markov process on this constructed probability space, and it starts at the measure nu, and it has the given transition kernels as its transition kernels. Now, before going into the proof, I want to warn you one more time. This does not mean that every Markov process with this data is this one here, or isomorphic to it. This is like Skorohod's theorem, where we can construct a coupling that has the right finite-dimensional distributions. It doesn't mean that every Markov process with this initial distribution and these transition kernels is exactly this one here. And that's going to be important because this will turn out to be a big unwieldy process on this huge path space. We would rather, when possible, have a different Markov process on a smaller path space, a space of continuous functions, for example. We'll get to that a little bit later. So the idea here is to match the required finite-dimensional distributions, which are determined by the transition kernels. Remember from the last lecture, we showed that if we have such a Markov process, then the law of any finite set of times of that process is given by this nice product formula in terms of the transition kernels and the initial distribution. So that tells us how to define a measure on the infinite product space, the path space, over S as follows. If we start with any finite set of times like this that happens to include 0, then we will define the measure mu lambda at those n+1 coordinates to be exactly this measure here. If we have a finite set of times that doesn't include the time 0, then it'll just be this measure here without the initial distribution. What we'd like to do is construct a measure, P, on the state space infinite product on the path space, whose marginals, that is, whose push forwards under the projections, are these mu lambdas. Why? Because if that's the case, then the probability that the vector xt0 up to xtn is in some fixed set B in the product Borel space in the sigma field is just going to be this measure mu lambda of the set of paths in S to the lambda, such that omega of t0 through omega of tn is in B. But of course, these are just the vectors x0, x1 through xn in the product of the state space, and that's exactly what we wanted. We wanted the probability that this vector is, equal to that one infinitesimally is given by this. So in order to satisfy this condition here, which will give me the right transition kernels, what I need is to construct a measure on the infinite path space with these as its marginals. The Kolmogorov Extension Theorem tells me that I can do that uniquely if and only if these measures satisfy the appropriate consistency condition. So let's check if that consistency condition holds. Now, actually doing so for all finite sets of times is a bit of a notational nightmare. I'm just going to do it in the case of a 3 and 2 time set here, and you'll see from here how it works in general. It's exactly the same, except notationally more intense. Suppose that I have a set of 3 times, t0, t1, and t2, and I consider the subset t0 and t2. The consistency condition tells me that in order to construct this probability measure that has these as marginals, if I take the probability measure on the 3 times set and push it forward to the 2 times set via the projection, I'm supposed to get the probability measure mu lambda prime of the 2 times set. Let's see if that's what happens. What we can see directly is that if I evaluate that measure on a product set, and of course it's good enough to evaluate these measures on product sets to get their full value on the product sigma fields, that's equal to, by the definition of the projection, mu lambda of B0 times the full state space S times B2. And now from the way we defined that marginal, I get that by integrating over B0, the initial distribution nu, and then integrating over S, the transition kernel, q from time 0 to time 1, x0 dx1, against the integral over B2 of q t1 up to t2 of x1 dx2. Now everything inside here is positive, and so by Tonelli's theorem I can reorder this integral however I want. So I'm going to do the integral over b0 times b2 up front, and that gives me the integral with respect to nu dx naught of the integral over s qt0 t1 of x naught dx1 q t1 t2 x1 dx2. Notice that I have the dx1 coupled with the x1 here, and I have t0 to t1 and t1 up to t2 precisely set up to apply the Chapman-Kolmogorov equations and get that this whole inside integral is just q t0 t2 of x0 dx2. So that means that this is equal to the integral over b0 of nu of dx naught of the integral over b2 of q t0 t2 x naught dx2. And that is how we designed the marginal mu lambda prime to act. And so there we have it. We have the desired consistency condition holding precisely because of the Chapman-Kolmogorov equations. Following this calculation with more intense notation, you see how we can show iteratively that the Chapman-Kolmogorov equations imply the desired consistency and therefore the existence of the measure p nu via Kolmogorov's extension theorem. So we have a probability space, and it assigns to our coordinate process the right finite dimensional distributions. However, that doesn't necessarily mean that the Markov property holds, as we established earlier. So we now have to show that this probability measure we've constructed gives the coordinate process the Markov property with respect to the filtration generated by the process itself. We'll see that it's actually baked into the recursive structure of the finite dimensional distributions that we've just produced. So fix any sequence of times, t0 up to tn, and let's call the penultimate time s and the final time t. Now let's let h be a bounded function of the first n variables and g be a bounded function of the last variable. Then if I take the expected value of this product of h of the process at times t0 through tn minus 1 times g of the process at time tn, and just to be clear, this expected value here means integrating with respect to the probability measure p nu that we've just constructed. Then that is, by the way we constructed it to have the right finite dimensional distributions, this integral here over Sn plus 1. Now here's what we're going to do. We're going to take the n factor here and incorporate it with the gn to write this integral as the integral over the first n of these, h of x0 up to xn minus 1, and then integrate that last variable together with the nth transition kernel here. That's the same thing as the transition operator q tn minus 1 tn acting on g at xn minus 1 against dx0, and then the product of the remaining n minus 1 transition kernels, qti minus 1 up to ti of xi minus 1 dxi. And let's just note that we called tn minus 1 s, tn t. And now look at this. This is a function of x0 through xn minus 1 integrated against the n minus 1 marginal at the times t0 up to tn minus 1 of the process. And so that is equal to the expected value by our construction of h of xt0 up to xtn minus 1 of this new function q of stg of xs. Now what have we shown? We've shown that if we call this random variable here y is h of xt0 through xtn minus 1, then the expected value of g of xtn, which is xt, times y, is the same as the expected value here of qst of g at xs times y. This is the averaging property, defining this as the conditional expectation of this relative to the sigma field generated by all of these y's. But these y's are all measurable with respect to the sigma field up to time s generated by x. And by a standard application of Dynkin's multiplicative systems theorem, this same property here from these is going to hold for all y that is bounded and measurable with respect to the sigma field generated by the process up to time s. And so finally we see that the conditional expectation of x of gt given fs is just q of st of g at xs. That's a function of xs, and so I can, with impunity, condition on the sigma field generated by xs. But this is equal to this conditional expectation. This sigma field is contained in that one, and so by the Tower property, this will just be the conditional expectation of this given xs, which establishes the Markov property and shows that the coordinate process xt is indeed a Markov process with respect to this probability measure. One final word before we sign off here. We've indexed the probability measure and the expectation by new because we're now going to shift the way we think about these things a little bit and think of the Markov process, instead of being a process, being a measure on path space. That is to say, we have the transition kernels. Those are our inputs. And given those transition kernels, we can form a measure on path space with respect to any initial distribution that we like, such that the process xt is a Markov process with that initial distribution and those transition kernels. That's going to be useful because we'll want to consider the whole family of Markov processes with those transition kernels, but varying the initial distribution to give us some extra rich structure to describe how Markov processes fit together.